Hello everyone, I am Himanshu Vasnani from Department of Mechanical Engineering. I am here to give you a lecture on subject material science. The subject code is ME207 from Unit 1, lecture number 5 in the series. Today's topic is surface and grain boundary defects, twin boundaries, stacking faults. Earlier, we have studied about various crystal structures and all things. Today we are going with the defects that can be found inside the structure. So today's objective will be the student should have a basic understanding of all these three kinds of defects and boundaries: the surface and grain boundary defects, twin boundaries, stacking faults, and students should have learned. And outcome will be students have learned the basics of surface and grain boundary defects, twin boundaries, and stacking faults and the various parameters affecting them. So start with this surface and grain boundary defects. You can say these imperfections of a structure which arise from a change in the stacking of atomic planes on or across a boundary and are two-dimensional. Okay, these are basically two-dimensional. The changes may be one of the orientations or of the stacking sequence arrangement. Okay, so the changes that you will see in these defects, it may be in the orientations or on the stacking sequence of the plane. I show in the later diagrams how the orientations they differ or how the sequence get disturbed. So the important kinds of surface defects are high angle and low angle boundary. The imperfections are internal. I'll show you how this high angle and low angle boundaries. I'll show you with the diagram. This stacking fault, how it looks, twin boundaries, how they look like. I'll show you all these three things with the help of diagram in which you will understand in depth what it does, how it looks like. Okay. Now I'll start off with the next slide. The external surface of a material is an imperfection itself because the atomic bonds do not extend beyond it. The surface atoms have neighbors on one side while atoms inside a crystal have neighbors on either side of them. Understood? Like surface atoms, what happens? They have some atoms on one side while the atoms inside the crystal they have neighbors on either side of them. I'll show you with the help of diagram. This diagram you can easily see. The surface atoms, how they get elongated, and the internal atoms they have support from inside. So they are different. Okay. Since the surface atoms are not entirely surrounded by others, they possess higher energy than that of the internal atoms. I repeat once again. Surface atoms that I've shown you here in this, the surface atoms, okay, on the boundary. Surface atoms are not entirely surrounded by others. They possess higher energy than that of the internal atoms. Like for most metals, the energy of the surface atoms of the order 1 joule per meter square. The internal surface imperfections are manifested by such defects as grain boundaries, tilt boundaries, twin boundaries, and stacking fault. The surface atoms they have higher energy than internal atoms. So the internal surface imperfections are manifested by such defects as grain boundaries, tilt boundaries, twin boundaries, and stacking faults. Okay, understood. See, external surface of a material See, it is also imperfection, but nobody can. You cannot go beyond that. Internals, they have neighbors atoms with them, internal atoms. So their imperfection can be caused. Okay. Now we'll go further. You understood the meaning? The internal surface imperfections are manifested by such effects as gain boundaries, twin boundaries, technical faults, and so we'll go with this. You can see in the diagram the external surface how it is elongated and the energy it has. Internals, they all are in the same sequence. They are not disturbed in shape and other things. Okay. Grain boundaries. Now, engineering materials may be either polycrystalline or single crystal type. This we have studied in the earlier lectures of crystal. What is polycrystalline? What is okay? Single crystal type. So, a polycrystalline alloys contain an enormous quantity of fine grains. Okay, a polycrystalline alloy contains an enormous quantity of fine grains. Grain boundary imperfections are those imperfections which separate crystals or grains of different orientation. Okay, in a polycrystalline aggregation during nucleation or crystallization. As the name said, polycrystalline means they have good amount of grains. Okay. Now when we talk about grain boundary imperfections, matlab something on the boundary of the grain, there is an imperfection. So these are those surface imperfections which separate crystals or grains of different orientation. Okay, so in a polycrystalline there may be different grains. So they separate orientation grains having different orientation in a polycrystalline aggregation during nucleation or crystallization. The shape of a grain is usually influenced by the presence of surrounding grains. Right. As I told you in the previous slide also, grains on the exterior and grains on the interior. Exterior grains have some possibility of movement because they have less neighbors or no neighbor, but the internal grains might have surround will have surrounding grains and their movement is not disturbed, so the shape is also depending upon the surrounding grains. The shape of a grain is usually influenced by the presence of surrounding grain. The lattices, the word lattices I have discussed earlier in the previous slides also. The lattices of adjacent grains are oriented at random and differently, that will be shown in the diagram later on, and a boundary between any two grains is essentially a transition layer of thickness 1 is to 5 nanometer. I repeat, the lattices of adjacent grains are oriented at random, okay, randomly they are, and differently, and a boundary between any two grains, boundary, grain boundary, any two grains, between two grains, essentially a thickness layer, just sorry, a transition layer of thickness of 1 to 5 nanometer. This layer may have a disordered arrangement of atom. This boundary, grain boundary imperfection. This may have a disordered arrangement of atoms, dislocation of clusters, and an elevated concentration of impurities. Okay, what grain boundary imperfections are doing? They are giving you those surface imperfections which we are already separated of by grains of different orientations in a polycrystalline. Okay, And what happens? Uh, the lattices may be of the adjacent grains. Okay, they already having a boundary between any two grains, which is essentially a transition layer of thickness of a certain thickness. And this layer may have a disordered arrangement of atoms and dislocation of clusters or an elevated concentration of impurities. Okay, there you can see in this diagram very easily. In the A on the left diagram, there are showing two grains, grain 1 and grain 2, and in between a boundary layer imperfection. See the name from the here, grain boundary imperfection. See how easily it is depicted with the help of the diagram what actually is. In the B diagram, you can see that it is having a low angle boundaries. There are arrangements which is showing this kind of a diagram. Now let's go further. Now in the grain boundaries, what happens? In grain boundaries, the atomic packing is imperfect, right? We've seen in the diagram. And between two adjacent grains, there is transition zone that is not aligned with either grain. Okay. Between two adjacent grains, there is a transition zone. You see in the diagram only. As a result, boundary grains in such cases cannot have a perfect complement of surrounding grain atoms. The mismatch of not mismatch with orientation of adjacent grain produces a less efficient packing of atoms among the boundary. So the atoms along the boundary have a higher energy than those within the grains. I repeat, the atoms along the boundary have higher energy than those within the grains. The higher energy of the boundary atoms is also important for the nucleation of this phase changes. And this is what interface come into practice, that the boundary between two crystals having different crystalline arrangements or different composition is called an interface boundary or an interface. Okay, you are having a boundary which is showing two different crystalline arrangements or different composition, that is called as interface boundary, that you should properly understand and that you should. Okay, this is the diagram just showing that how this grain boundary comes into practice. Okay, you can see the area of disorder at the grain boundary. Let's go further. The atomic lower atomic packing along the boundary favors atomic distribution when the orientation difference between neighboring grains is more than 10 degree to 15 degree. Boundaries are called as high angle grain boundaries that I shown you in the diagram. High angle grain boundaries. So it is giving that when the orientation difference between the neighboring grains is more than 10 to 15 degree, boundaries are called as high angle grain boundaries. Now each grain in turn consists of subgrains or block, and regular structure. So subgrain boundaries are formed by walls of dislocation which drive a grain into a number of subgrain or blocks. Like in this B diagram, it is depicting them only having low angle boundaries. It is saying that each grain in turn consists of subgrains of blocks, and a subgrain is a portion of a crystal with a relatively regular structure. So these subgrain boundaries are formed by walls of dislocation which divide a grain into a number of subgrain or blocks. The angle of misorientation maybe maybe called as a low angle. Angular misorientation between adjacent subgrains are not very large, not more than 5 degree, so that their boundaries are termed as low angle. Low angle boundaries can also serve as places of accumulation of impurities. From this diagram, you can easily understand what is being said. Then tilt boundaries. This topic is important because in various structures, if you will go with the microscopic view, you will see that there are tilt boundaries in which you are found that there is some kind of surface defect. The tilt may be of some degrees, maybe 5 to 10 degrees, whatever is the disruption that is seen in the boundary. Okay. Uh, the dislocation, what you are saying, it may be a single dislocation or maybe a arrow of arrays of dislocation, and which can be well shown with the help of Bugger vectors. So in the right side, you can see that there is a boundary written and it has a tilt. Uh, in the bottom, there is written an angle theta, and on the right side in the diagram, it is in grain 1, and on the left side, it is written grain 2. There is a value of small b. Small b is denotes of magnitude of Bugger vectors. Bugger vector I have told you in the previous slides. And there is also a term called capital B, which is the average vertical distance between dislocations. So here in the tilt boundaries, we can say that this is another type of a surface defect, which is called as low angle boundary, as the orientation difference between two neighboring crystals is less than 10%, sorry, 10 degrees, 10 degrees. That is why disruption in the boundary is not so drastic as in high angle boundaries. This type of boundary is associated with relatively little energy and is composed of edge dislocations lying one above the other. Okay, because here very little energy is associated and is decomposed edge dislocations. I told you about edge dislocation. Something is entering, an extra layer is entering. Okay, in the, you can say, structure. So it is called as edge dislocation, lying one above the another. So in general, one can describe the low angle boundaries the suitable area of dislocation. You can see that how different layers are entering from top to bottom in the diagram. The angle or tilt theta, that is b upon d, where b is the magnitude of Bugger vector and b is the average vertical distance. So here you can easily understand that how tilt boundaries can be taken out. So we'll go with the next. Then twin boundaries. Twin something similar. Twin, maybe a mirror reflection of one portion to the another portion. It can be called as twin boundaries. So this is another planar surface imperfection. You can see in the diagram this is shown that there are twin planes with the help of TT, and twin boundaries are shown, and on the right hand side, left hand side, there are perfect region, and in the between there is twin band or distorted region having twin boundaries. From the figure you can easily see that. So here, yeah, we can go with that. This is another surface, sorry, planar surface imperfection. The atomic arrangement on one side of a twin boundary is a mirror reflection of the arrangement on the other side. See, these all you can say images. This can only understood when you go with the microscopic study of you. You might be feeling that it is kind of a structure. How we can read that? But whenever you go with the microscopic study, it will tell you that okay, these structure exist. These structure, it may be termed as a defect somewhere. So we should be aware of that. So twin boundaries can be defined as another planar surface imperfection and the atomic arrangement on one side of a twin twin boundaries other side and in between there is a twisted band. Then twinning may result during the crystal growth or deformation of the materials uh, because twin boundaries they occur pairs. Obviously, two are there, so it occurs in pairs such that such that the orientation change introduced by one boundary is stored by the okay. Whenever there is a deformation of material, or you can say there is a crystal growth, then you will find that these kind of twin boundaries they occur, and normally they occur in two, maybe in pairs, and so such that the orientation change introduced by one boundary is restored by the other. So here you will have a twin boundaries planar surface imperfection, which is normally studied with the help of microscopic view. Now we go further. Twin boundaries. Here the region between the pair of boundaries is termed as twinned region. The region between the pair of boundaries is termed as the twinned region. One can easily identify twin boundaries under an optical microscope. I was telling you also that these structure can be easily studied under a microscope, because what happens, you can easily magnify okay. See, twins which form during the process of recrystallization, we'll study later on in the coming lectures. Twins which are formed during the process of recrystallization, that is in the process of mechanical working, are known as mechanical twins. Whereas twins formed as a result of annealing after plastic deformation are known as annealing twins. See, annealing is also a heat treatment process. Annealing, annealing? Annealing is a kind of a heat treatment process. We'll coming in the study in the coming chapters. So whenever we perform an annealing process and whenever there is a plastic deformation, then if we get twins, again like we get a twin boundary, then it is called as annealing twins. And maybe twins which form during the process of recrystallization, that is after mechanical working, they are called as mechanical twins. These are why it is said, because these are such terms used to identify that okay, we got a twin boundary and we get a twinned region. So with the help of microscope, you can study that where in which structures you can easily get twin boundaries with the help of a twin region, and uh, it will be helpful to you to study the structure of the materials. Now, the after this we are going with stacking faults. Now, stacking faults, as you can see in the diagram, there are layers of, and in the layers in the center there is some kind of curve, and then some disturbance, and then again curve, and then again straight lines. So stacking. Okay, then we will study this. This is a part of an atomic plane confined between dislocations, and in which regular order of alternation of atomic layers is disturbed. I repeat, this is the part of an atomic plane confined between dislocations, and in which the regular order of alternations of atomic layers is disturbed. The you can see in the diagram there is an order B A C B A B C A B. Okay, this order and the atomic layer are getting disturbed in between, and that also getting normal. Okay, so the atomic plane is having some dislocations and then again it is getting undisturbed. This is stacking faults. This type of faults arise from the stacking of one atomic plane out of the sequence on another while the lattice on either sides of the fault is perfect. I repeat that how they arise? They arise because uh, stacking of one atomic plane out of the sequence on another while the lattice on either side of the fault is perfect. Okay. For instance, in FCC, that is face-centered cubic structure, lattice alloys, closed packed atomic layers are normally in an alteration of ABC, ABC, ABC. This is the sequence it is showing, and this is a normal sequence. This is a diagram. Then, on passing through a stacking fault, their alternations may change. For instance, from ABC to BCA, BC. Okay, the BC-BC alteration is typical of an HCP lattice, hexagonal closed stacking lattice, and therefore the stacking fault is present as it was in the structure of an HCC lattice. What happens that you were having FCC structure after passing through a stacking fault, the new you can say alternation, it represents normally SCP hexagonal closed stacking lattice. So after studying through a microscope, we found that a thin plate of HCP lattice was present in the structure of HCC lattice. So that is something different. And how a thin plate of HCP lattice was present in the structure of an HCC lattice. So this is kind of a stacking fault that you have found out. So here also this figure shows the faults in the structure of FCC lattice crystal. So here the stacking sequence of an ideal FCC crystal is described as ABC ABC, and the stacking fault may change the sequence of ABC AC AB. Okay, so this is kind of called as a stacking fault because here you study the crystal structure and then you found out. One more thing in that. Okay, yeah, one. There was an equation in this also. Let me get to you. Yeah, surface defects, these influence the mechanical and physical properties of the material. Especially large importance are grain boundaries. And there is an equation giving that rho y is equals to rho naught plus kd raised to the power minus half, 1 by 2. So the yield strength rho y is associated with the grain size d, small d, by the relation this that rho y is equals to rho naught plus k d. D is the grain size raised to the power minus 1 by 2. Though rho naught and k are constant for a given material, whatever material you are using, they are constant for that. With finer grains, the material has higher yield strength and toughness and is less susceptible to brittle failure. With finer grains, the material is less susceptible to brittle failure, has good toughness and higher yield strength. The size of subgrains has a similar low, less strong effect on mechanical properties. Because you know that the surface defects they influence the mechanical and physical properties of material. So here the grain boundaries will also affect. Okay, so we go further. Slip systems. Now slip systems are important when you are going for studying a dislocation. Okay, how they are important that we will study in the coming slide. That dislocations do not move with same degree of move on all crystallographic planes of atoms and in all crystallographic directions. Ordinarily, there is a preferred plane, and in that plane, there are specific directions along with dislocations, motions. This plane is called the slip plane. Okay, it follows that the direction of movement is called the slip direction. What happens that uh, if you have a crystal, and in that case there is some degree of movement. Okay, so this movement they normally they have a preferred plane in which this dislocation takes place. So that is called as slip plane in which dislocation motion it happens, and the direction of movement in which this plane moves, it is called as slip direction. This combination of slip plane and the slip direction is termed as slip system. I repeat, understand system. The plane in which the dislocation will happen and the direction in which the movement will take place. Combining both these things, it is called as slip system. Okay. Now the slip system is it depends upon the structure. What is the structure of the crystal? Okay, that means that if the structure is less dense, it will have less planar density. If a structure is more dense, more atomic packing, then it has more planar density. So the slip system it depends on the crystal structure of the metal. Okay, for a particular crystal structure, the slip plane is the plane that has the most dense atomic packing. That is, it has a greatest planar density. Now we go further. You can see in the diagram, okay, that a point A, capital A, is having a location of 111. That is the we have studied about lattice point. So in this we have this is a location of 111. Slip system shown within an FCC unit cell. Okay, the 111 plane from figure A and three slip directions you can see through the arrows in figure B. Okay, within that plane comprises possible slip system. Why? Because they may have the maximum density. Okay, so through this diagram, we are able to understand that if this is a face-centered cubic structure, see this is structure that has been studied under microscope and many other structures similar to that have been studied and found out after this study that okay through this slip system may happen. So they have found out a plane through which this system happens in a FCC itself, and they have shown this with the within that capital A111 through this slip system is shown in the FCC cell. Okay, and the possible slip system they have also shown that plane also with the help of arrows in the figure B. Okay, you can see that A, B, C, D, E, F in the figure B, and with the arrows going from A to B to D, then D to E to F, and then from A to C to F. Okay. Now the slip direction corresponds to the direction in this plane that is most closely packed with atoms and that has the highest linear density. Okay, this is the direction that was showing no in this diagram direction A to B to D, then D to E to F, and A to C to F. Okay, with these direction, these slip direction they correspond to the direction in this plane that is most closely packed with atoms. That's the highest linear density. Like for example, the FCC crystal structure in a unit cell which is shown in the figure. Okay, this is the set of plane, the triple one family, 111 family, all of which are closely packed. Then a point A that is shown on the top in figure A. Type plane is indicated in the unit cell in figure 6b. This plane is positioned within the plane of the page in which the atoms are represented as touching nearest neighbors. Okay, you can see in the diagram that here on the right hand side it is showing that atoms are easily in touch, and on the left hand side it is shown with the help of a plane 111. Okay, so they are depicting one thing but in two different ways. Okay, in two different. Now, yeah, okay, so this is the same diagram. The slip occurs along type directions within the triple one plane as shown by the arrows in the figure. Then this triple one plane, this represents the slip plane, and the directions that is shown in the figure, uh, the direction combinations or the system for FCC, because they both make the, the slip system. In the figure B that is demonstrated, uh, that demonstrates a given slip plane may contain more than a single slip direction. And the several slip systems may exist for a particular crystal structure. It depends upon the structure. The number of independent slip systems represents the different possible combination of slip tails and direction. See, this depends upon the past studies of the research. Okay, or because you have to find out which has the maximum, you can say, density. So in that case, you have to understand that where the slip system will lie. Okay, and you have to find out the possible combinations of planes and directions. So it depends. For example, a face-centered cubic, there are 12 slip systems, four unique triple one planes, and within each plane, three independent directions. How they have come to this result, this example? Because they have studied this under microscope. They have done their part under microscope. So through this, they are able to get it. Okay, they have they have database, and they find out that there are 12 slip systems within this FPC structure. Okay, that's it further. Now this is the slip system for face-centered cubic, then for body-centered cubic and hexagonal closed packing structure. See, these are common structures that have been researched and worked upon again and again, and also some of the common metals are also named under that. So they enough, yeah, you can say sufficient amount of research is done in these three kinds of structures that have been used for these showing different kind of metals. Like for face FCC structure, you can go with these metals like copper, aluminium, nickel. So you can see that the slip plane is 111 that I've seen in the diagram also, so direction 110, and number system that is 12. And in the BCC structure, that we have alpha, iron, molybdenum, and you have a slip plane of 110 and of 211, 321, showing having different directions, a number of system of having in the, you see that 12, 12, 24. Then the HCP structure, hexagonal closed packing structure, you have different things of cadmium, zinc, magnesium, beryllium. So they have a different slip plane having different slip direction and number of slip systems, 336. So in the table you can easily see that different structures have different slip systems. So it is helpful for them. Now slip in single crystals. Now as mentioned previously, edge, screw and mixed dislocations. They move in response to shear stress. applied along a slip plane and in a slip direction. Even though an applied stress, you can say it may be purely tensile or compressive, shear component exists at all but parallel or perpendicular aligned to the stress direction. Now these all you can say systems, these are termed as resolved shear stresses and the magnitudes. It depends not only on the applied stress but on the orientation of both slip planes and the direction within that plane. Okay, now we have formula that is rho r is equals to rho cos phi and cos lambda. So this is having both the angles that are not equal to 90 degree. Okay, so this system should be clearly understood. Now here in the figure you can see that there is a geometric relationship between tensile axis and slip plane and slip direction using calculating the resolved shear stress for single crystal. So here you can easily understand the different the slip direction and the normal to slip plane. Here in the center, how the force is coming and the angles cos phi and cos lambda. So you can easily study that. Okay, now we'll go further. In response to the applied tensile or compressive stress, yep, I go with also faster because I have to complete the lecture. Or compressive stress slip in a single crystal commences on the most favorably oriented slip system when the resolved shear stress reaches some critical value, termed the critical resolved shear stress. And the single crystal it plastically deforms or yields when you have a value in the you can say the formula it is given that the rho y is equals to you can say the magnitude of applied stress. So you can easily understand the formula for yield strength rho y. It is given that 3 cross upon cos of phi upon cos of lambda. So here you can see that the minimum stress necessarily to introduce a yielding occurs when a single crystal is oriented such that uh, these angles are equal to 45 degree. Okay, so this is good. Then deformation by twinning. Twinning is you can say the formation of twins. This I think I'll cover in the next lecture because I have to complete my quiz also within the time. So I'll cover this thing in the next chapter. Okay. So let me start with the MCQs. So for the first question, I'll say that these imperfections are those surface imperfections which separate crystals or grains of different orientation in a polycrystalline aggregation during nucleation or crystallization. So what do we call this kind of imperfection? We can say that this is a kind of a grain boundary imperfection that we studied in the previous slides also. Then the second question comes that the boundary between two crystals which have different crystalline arrangements or different composition is called an interface boundary or commonly called as you can say it as an interface imperfection. We have studied in the previous slide also what we call an interface and what do we call as interface imperfections. Okay, so we can go with that. Then the third question is that when the orientation difference between the neighboring grains is more than 10 degree to 15 degree, then boundaries are called as this angle will go for high angle grain boundaries. We know that. Okay, that is okay with that. Then the fourth question will come that this is another type of surface defect called as low angle boundary as the orientation difference between two neighboring crystals is less than 10 degree. So this is called as tilt boundaries. Okay, tilt boundaries. I've shown you with the help of a diagram also this tilt boundaries. Then fifth question, how are the point defects classified based on the source of atom? So you can say this was kind of intrinsic and extrinsic kind of a thing. Then sixth question is that these defects influence the mechanical and physical properties of materials, especially large importance are grain boundaries. We can go with the surface defects that we have studied in the lecture. Yeah, surface defects only we have studied in the lectures. Okay. Now in tuning, the amount of movement of each plane in the tune region is proportional to its distance from the tuning plane. How then therefore a mirror image is formed across the twin plane. Is it true or false? Remember twinning two common same images, one on either side between a twin region. So it is called as it's true. Sorry, it's true. In the measure there is a distorted region in the center and the both the sides you have same region. And the eighth question, it is a movement of atoms in the lattice resulting in a division of lattice into two parts which are symmetrical but differently oriented. It is called as twinning. We have studied tuning in this question also and then understood this in MCQ also. Now, ninth question, stacking fault is a part of atomic plane confined between dislocations and in which the regular order of alteration of atomic layer is disturbed, which is true, obviously. And last question, tuning may result during crystal growth or deformation of materials. Twin boundaries occur in pairs such that orientation change introduced by one boundary restored by the other. It is true. So we have studied all the kind of defects that is there along with the slip systems. These are normal kind of defects that are found, but these you can easily understood if you are studied under microscope, so that you are able to identify these kind of things. So these are the reference books which you can study, from which you can study if you want to have more kind of reading material if you require. These are promising books, so you can go with them. And I hope you like today's lecture. And thank you all for listening to me and for uh, having me. Thank you very much.